HIMT, Hindustan Institute of Maritime Training.
Static stability deals with vessel in static position. That means whether your vessel is in upright or any particular angle. You just look at what is the force acting on the ship at that point and from which positions they are acting. In mechanics, statics is about effect of a force on a structure. Like suppose a object is not moving, I apply a force. I can bend it, I can pull it like this. So in applied mechanics class, you would have solved numericals where you find, you get different shapes. They'll say load is so much, find the force on the beam. Different structure. That is called static. Dynamics is where you look at force in a different way. That force and its relation to motion. That when I apply a force, an object will move. So you write that equation: force equals mass into acceleration plus what?
Friction.
All the opposing force. We did that before, right? Force equal mass into acceleration plus the opposing forces. That is dynamics. When you say work done is force multiplied by distance moved, that is dynamics. So dynamic stability of the ship looks at these points. Are you understanding? So you say, so what it means in static stability is like taking a still picture. My ship is at 20 degrees. What is happening to my ship at 20 degrees at this point? What is the force acting? What is the moment that is coming? Dynamic stability will mean how did it reach here? How did the vessel reach 20 degrees? How much energy has to be spent to bring the vessel to 20 degrees? That is the principle. And in mechanical motion, we have done this before also. Principle of inertia always comes. If you move an object, you have to do work. And where does the work go? If you lift a bag and keep it on the table, what is the amount of work you do?
mgs.
If you lift a bag which is lying here and you keep it here,
mgs.
the force you have to apply will be
mgs.
M into G is the minimum force you have to apply. Okay? That is called, it will move without any acceleration. At uniform speed it will come. But that is the minimum force you apply. M into G multiplied by height, force into distance is the work. Right? Where did this work disappear? Where does it go?
It goes in body.
It becomes stored in the bag as potential energy. So potential energy formula is also mgh. Work done formula also is mgh. Now you take the same principle to the ship. To make a vessel to go from upright condition to inclined condition, don't think force is required. You have to say work has to be done. Force required is there, but dynamic stability looks at work energy. So you have to see how much work has to be done by the external medium, whether it is wave or whether it is wind, how much work has to be done by that. That is called dynamic stability. And mechanics principle is same. It is always force into distance. Okay, but ship rolling is not translation; it is rotational. You have to rotate. So how do you do calculations of work done with rotation?
Roll.
When something rotates,
Omega.
how much work is done? It is based on this principle.
R and
I'm turning something like
R
this.
omega.
So I apply a force here at a radius r, right? And then it inclines by one, or rotates by
Angle.
small angle d theta, and you get it moves at small distance x. Moves by small distance x. So what is the small work done? Small amount of work done is force into distance. Okay? Force into distance. So you will say F into dx. Then you write the next step. It is F into dx. You divide by radius and multiply by radius. Both sides.
Torque.
Then what does it become?
T dx by R.
One is F into R, other is
Dx by R.
dx by R. So what is F into R? F into R.
Torque.
F into R equals, you can call it torque, or you can call it moment of force, right?
T d theta.
And what is dx by R?
D theta. Sine.
Dx by R is d theta in radian.
T d theta.
Definition of radian is arc length by radius. Length of the arc divided by radius is angle in radian.
Radian.
So d theta is
Dx
dx
by R.
by r. So your equation will turn out like this.
T d theta.
It becomes
T into d.
torque into d theta. It is from here you get the formula torque into omega is power. How do you go from work to power?
Do.
Power is rate of doing work. So you divide by
dt.
dt. This is power. If you here you divide by dt, what do you get? D theta by dt is
Velocity.
omega, angular velocity.
Velocity.
So you get power equal torque into
Omega.
omega. And omega is 2 pi n by 60.
2.T by 60.
So that is how it comes. So power, rotary power equals
2.T by 60.
torque into 2 pi n by 60 comes from here. But ship is not going to go round and round. So we are not looking at power. So what are we interested in is only the amount of work done. Understood? Ship cannot be rotating like this and going down. But how much work is required? So you will not bother about the time part of it. So if a ship is going to, from an upright condition, if a ship is going to incline a little bit, how much work is required to be done? That is the principle. So you think of a ship, if you think of a ship which is upright and heeling moment is making it to go like this, right? Will something oppose the motion? Righting moment will come. So the minimum heeling moment will be the righting moment. Like that is the amount you have to do. It's just like saying the minimum force I have to apply is the weight of the bag. When I'm lifting a bag, the minimum force you have to apply is the weight of the bag. So you got a vessel which is going to go like this, the heeling moment. Righting moment is going to be opposing it. And again, overcoming the righting moment, the vessel displaced by a small angle. What is the small angle? D theta. So the work done principle is, if you are going to write small work is torque into d theta, or you write moment of the force, right? Moment of the force into d theta. So the way it will compose the ship is healing moment opposed by rating moment. I've got this force is acting dz. This is the rating moment which is acting like this, and the small angle d theta, the inclination which happened. So what is the work done? If you do the same thing for the ship,
G Z
it becomes
W W V Z.
the d theta will be
G M
what is the moment is
G Z
gz
into W
into
W.
displacement force. So that is the rating moment. Clear? That is what you have to overcome to make the ship. See, the wind is pushing like this, ship is opposing like this. So the righting moment is the torque you have to overcome. And what did you see for applied torque and resisting torque? If they are equal, you will get uniform speed. That the rotation, initial calculation is the vessel is rolling with uniform speed, no acceleration, just uniform speed like that. So for that you start with this calculation, gz into displacement. This is the moment. For the rotating shaft it was written like this, dw equals torque into d theta. Here this is the torque we are looking at, multiplied by d theta. Then what will be the work over a large angle?
Integrate.
You have to integrate. So a vessel is rolling from upright to 20 degrees. Then it will become theta 0 to theta 20. You have to integrate for so much. So what are you going to get here? Out of these two, which is constant?
Displacement.
Displacement is constant. So you can pull that out.
G Z.
Gz is not constant. So you get integral of gz d theta from 0 to 20. Gz is not a fixed value, it is a variable. You saw the shape like this. And d theta. So this formula says if you are interested in finding the work done by external force, work done by wave or wind, which is taking a shift from 0 degree to 20 degree, you have to find this way. You take the weight. If you want in SI units, you will be converting everything into SI units. So from ton, you have to put 9.81. So that you turn it into Newton, you can turn it into Joule, kilojoule, megajoule, like that you can do. But the principle is you take the weight of the ship, integrate gz against theta from this limit to this limit. Right? So once again the question comes, can I do this integration? To do by calculus, what is required? To solve this by, I need the equation. But what did you see about the gz curve? Does it fit any mathematical equation? It doesn't fit. But you have a graph. So what is the connection between integration by calculus and integration by
Area under the
graph is?
Area
Under the curve is same as integration. Understood? So if you want to solve by calculus, you need the equation. But we don't need the equation if you have the graph. So this whole thing can be turned as
area under the GZ curve.
work done. Okay, it will become like this. Work done to work from
0 to 20.
This example, what are we saying?
0 to 20.
0 to 20 degree will be equal to displacement multiplied by this part, which is area under
GZ curve.
GZ curve. From here to here. Area also always has to be specified from here to there. Area under GZ curve from 0 to 20 degree. This area will be in meter radian. Displacement will be in ton. To turn into SI unit, you use 9.81 all those. So this is a value which can be calculated for a ship. If you see any ship at 5 degrees, 10 degrees, 30 degrees, you are finding out what was done to bring the ship to this side. How much work was done to bring the ship to this side. And if the area is more, what is the benefit then?
More work has to be done.
More work has to be done, which means the vessel can resist rolling more. That is the meaning. The wave has to be stronger to roll the ship. That is why the intact criteria requires looks at area in 3 different ways. That there is a requirement that the GZ curve should have so much of area. So this value is called dynamic stability, or some books will call it dynamical stability.
Which one is it? This work done?
This work done. So if you normally say what is the static stability of your ship at 20 degrees, you usually will mean what is the GZ value at 20 degrees. Are you understanding? Tell me about static stability of your ship at 20 degree angle. Then the answer will be my vessel's GZ value at 20 is this many meter. But if you are asked, tell me what is the dynamic stability of a ship at 20 degrees. It means this much of work has to be done to bring the ship to the 20. So dynamic stability will be expressed in terms of joules. If you are talking of SI units, it will be in joule. Otherwise, normally it is said in meter radian. Ton meter radian. Weight also now. Displacement. Ton meter. Radian is included because radian actually is no unit because it is meter by meter. But normally it will be said ton meter. Ton for displacement and displacement. So what I am saying is go beyond saying static stability means ship is in port, dynamic stability means ship is at sea. This kind of answer even a pre-sea boy will give. Are you understanding? So dynamic stability means you are looking at in a different way. And by the principle of mechanics, work done will get stored as energy in the object. So this much, whatever work is done by the wave is actually stored in the vessel as energy. And actually it is this energy which brings the vessel back. It is like when you say pendulum is moving, what brings the pendulum back to this position is the potential energy it has converts to kinetic and brings it here. That is the actual principle. Because why energy is important is because only when you get into energy, you can talk about damping. What is damping?
Reducing
Yeah, and all those calculations are done in terms of energy, not by force. So when the vibration class or anywhere you talk about initially you will start with distance and force and all of it, but the calculation has to move on to work done and energy. So if a vibration is stopped, it is because the energy is dissipated by damping. So if a vessel which is rolling comes to a stop, it is because the energy has to be dissipated. So that is the reason you have to move to energy and work done to understand how it should behave at sea. Understood? So static stability is related to force. Dynamic stability is about work and energy. And the real behavior of a ship at sea has to be judged only by this. So based on this, there are criteria called wind and weather criteria for a ship. That is where, in simple English, what it means is, if you are building a ship, you have to build a ship to withstand so much of rough weather. So there is one criterion called heavy weather criterion or wind and weather criterion. Okay. But what I am saying, you all should take little bit of interest. You are sitting in a ship and going somewhere, no? You should take a little bit of interest in saying, is your vessel safe to go through rough weather? Or you leave it everything to God and go? God or nature or whoever you believe in. So the vessel has to be built according to some requirements. One of the requirements is called heavy weather criterion. So in heavy weather criterion, it will deal entirely with this part called dynamic stability.